Hello and welcome to Lesson 2A, Introduction to Functions. We're first going to look at finding the domain and range of functions and relations. The set of all possible values of x of a function comprise the domain of the function, while the set of all possible y values comprise the range of a function. To identify the domain of a set of options or mappings, we just list all the x values, omitting the repeated values, and the same thing with the range. We're going to list all the possible y values, omitting the repeated values. So here in part A, I'm going to list all of these x values as my domain. -3, 0, 1, and 7, and notice I'm writing them in order. And then for the range, I'm going to list all the y values, which were -4, 0, 2, and 5. And notice I rewrote those from least to greatest. Now when we have a mapping, and this down here is called a mapping, we do the exact same thing. To determine if something's a relation, what I want to do is I want to basically write down every single pair of points that are produced by this mapping. And so we simply follow here, like -5 maps to -3. So that means we'd have the point -5, -3 in our relation. 1 maps to 0, so we would go 1, 0 in our relation. Then 3 maps to 4 and 3 maps to 9, so it shows up twice, 3, 4 and 3, 9 in the relation. And then 6 maps to 1, and that's my last point in our relation. I'm running out of space here. Now we're going to list the domain and the range. And guys, your domain are all your x values, which you could pull out of the points we just listed, or you can pull out of that column there. And notice 3 shows up twice, but I only list it once in my domain. Then my range are all of my y values. That would be this column here, or -3, 0, 1, 4, and 9 are all of my y values. And notice there were more range values than were domain values because we had a repeated x, but no repeated y values. You can also name the domain and range of a relation from its graph. To do this, we identify the points that make up the relation, then name the x values and the domain and the y values for the range. So let's look at a graph. These are singular points, so we only have 4 items in this relation. And so my relation is just -4, 1, -2, 0, 0, -1, and 2, -2. So my domain are all of the x values. So go ahead and list those x values. All right, and now guys, go ahead and list the range. All right, take a minute and check your work. All right, I want all of you now to look at B. I want you to list the relation, then list the domain and the range. Again, guys, we don't repeat repeated values in our domain or range. So take a minute and do that. Okay, take a minute and check your work. Notice the range, because we had repeated values in the range, the only values we list are -1, 0, and 3. We don't list any of those twice. All right, so now let's take a look about how we would talk about domain and range when we have a function that is more continuous. So looking at the following functions, it's not actually possible for us to list every single point represented because we have points on these nice big dots, but we also have points at the fractional values. So there is a value for 0.1, there is a value for 1.99, and it's impossible for me to go through and list all of those values. So what I do instead, rather than listing my domain as a series of discrete points, I'm instead going to list the domain and range as an inequality that shows a range of values that we can take. So when we're focusing on the domain here, that's my x values. So I look from left to right to figure out my domain. The furthest left we go here is -2, and the furthest right we go is 4. And you'll notice we have closed dots on both of those. So we are actually able to equal both -2 and 4. So I use the less than or equal to symbol. And we've got an x in between them because those are all the values that x can take. X is between -2 and +4. Then on my y values, the lowest we go is 0, and the highest we go is 3 because, guys, y is vertical. So my range goes between 0 and 3 with my y. I'm able to equal both of those points, so I use the less than or equal to symbols. So that's how I do my domain and I do my range. Looking over on this guy, I'm going to let you guys do this one in the middle here. So take a minute and try it on your own. Now check your answer. Notice when I'm talking about my domain and range, when we've got an open circle like that, we use the strictly less than symbol because we can't actually equal the x value of 3 or the y value of 1, but we could get infinitely close to it. So we denote that with a different symbol. All right, let's walk through this next one together though, because it's a little bit different. Again, I'm going to look at my domain first. Those are my x values. The lowest we go to the right is -3, and the highest we go is -2 and +2. So my x value, my range, is between -2 and 2. And if you notice, we have open circles on both of those, so those are both strictly less than symbols. Now my range on the other, that was my domain. What am I doing, guys? Give me a second. Boop. Let's change that to domain. My range, on the other hand, is going to be a little bit different. It's the highest value and the lowest value. The highest this function goes is 3, and the lowest this function goes is -1. So our range is between -1 and 3, and range is always y values. Now notice the lowest value, those are both open circles, so it's a strictly less than symbol. But the highest value, it can actually equal 3. The function is actually going through that point, so it's less than or equal to. That's how we do domain and range on a continuous function. All right, for continuous functions, you need to use the inequality to describe the domain. It can have 1 or 2 endpoints. For one endpoint, we have the lower bound is less than x is less than the upper bound, and for my range, the lower bound is less than y is less than the upper bound. But when we have 2 endpoints, we might have something else happening. So let's take a look at some examples where we have infinite solutions possibly on some of these. Now, the functions graph below, these are different than the previous functions we've seen because they go off to infinity in one or more directions. So if we're looking at the smallest or highest value in the graph and it has an arrow, that indicates that the function does not have a smallest or highest value. It is instead approaching positive or negative infinity. For graphs that have neither a lower bound nor an upper bound, we may list the domain or range as all real numbers and use the capital R symbol. I'll show you guys how to write that. So let's take a look at this first example here. I'm looking at my domain, and again, domain goes from left to right. My furthest to the left, I'm hitting an arrow. Furthest to the right, also hitting an arrow. When I've got 2 arrows, that means my x values can take any value I want to on the number line. So that means that my value for x, the domain, is all real numbers. And I write that by doing a capital R with 2 bars on the bar for the R. Now my range is a little bit different. When we consider the lower bound, the lowest we go is 1 or -1. But the highest we go, boom, again, we've got arrows happening here. And whenever we hit an arrow, that means we're approaching infinity. So rather than writing this as 1 is less than y is less than infinity, I don't like writing it like that. There's an easier way to write it. I can instead say that y is always greater than or equal to 1. That my y values start at 1 and go up from there. So we have a domain of all real numbers and a range of y is greater than or equal to 1. Here we have a line, and if we look at my domain, as I'm going from left to right, I'm getting arrows on both ends as I go from left to right, which means that my domain here is all real numbers. We can plug any x value in to this equation and get a result. My range is also similar. As I go from the bottom, I get an arrow. As I go from the top, I get an arrow. My range here is also all real numbers, which means I can have any y value on this graph. All right, now let's take a look at this last graph. I want y'all actually to try this one on your own. So take a minute and try to solve this one. My domain on this problem ends up being all real numbers because as we look from the left to the right, we get arrows on both sides. My range, on the other hand, the highest we go here, up here on the y value, is 4, and we can take any value lower than that, so we get y is less than or equal to 4. Now we're going to talk about, is it a function? In order for a graph, equation, or set of ordered pairs to represent a function, each input value may only correspond to one output value. For example, if 3 is in the domain of f, then f of 3 may not have 2 values. What does that really look like? Basically, I look to see if there are any repeated x values. Every x value should only have one outputted y value. So here, I've got 3 separate x values. 0 maps to 5, 1 maps to 5, 2 maps to 5. There isn't a second 0 in this list, so this guy is a function, okay? Because you're going to look for repeated x values. Whereas here, 2 maps to 5, 2 maps to 4, and 2 maps to 3, 2 is mapping to all kinds of things. This guy is not a function, because f of 2 has multiple values. All right, let's move right along. You can also, when you're looking at a graph of a function, use the vertical line test. If no vertical line can be drawn so that it intersects the graph at more than once, the graph is a function. So when I do this, boom. Oh, I should have done that more vertically. Sorry, guys. Boom. It intersects twice. Not a function. Whereas here, no matter where I draw a vertical line, we're only connecting once. So this guy is a function. I want y'all now to do E and F for me. So if we take a look at E and F, E is not a function because there are multiple instances where your vertical line test fails, whereas F is a function. And now let's talk about G and H. Well, G is a linear equation, y equals 2x. If we were to graph that, it would look kind of like this. And if we look, a straight line is always a function. It passes the vertical line test. Whereas when we look at H, H is different. If we actually look at x to y, we make a table. If I plug 4 in for x, I would get 2 for y, but I also could get -2. Because 2 squared is 4 and -2 squared is also 4, this guy is not a function. If we actually graphed him, he would look like this. He'd look like a sideways parabola. He is not a function. So let's now talk about function notation. Functions express the dependence of one variable quantity on another. F depends on x is written as f of x. So just rewriting things in function notation is usually pretty much as easy as solving for y, then replacing the y with f of x. So for example, this guy would be f of x equals 2x squared plus 3x minus 7. On B down here, I'm first going to solve for y, which when I solve, I get y equals -1/2 x minus 2. Then I replace the y with f of x. So we'd say f of x equals 1/2 x minus 2 is my function notation. If we want to evaluate a function, all we do, if we ask for g of 2, that means take the -2 and put it in place of the x's. So g of -2 is equal to 3 times -2 minus 2, or that's -6 minus 2 is -8. G of 0 would be 3 times 0 minus 2, or -2. G of m would equal 3m minus 2, and that can't be evaluated further, so that'd be my final answer. I want you guys now to do A and B on question 3. Again, watch your exponent laws. -3 squared is 9, minus 1 is 8. F of 0 gets you -1. Now to find f of a minus 2, that means I'm going to plug in a minus 2 everywhere I see an x. Again, guys, use a parenthesis when you're plugging in values, because this tells me now to square that polynomial there. So when we square things, we multiply them by themselves. And when I do that, I'm going to FOIL it out. I get a squared minus 2a is minus 4a plus 4 minus 1, or a squared minus 4a plus 3. All right, guys, I want y'all to take a moment and solve A and B for number 4. So when I plug in for A, I get 1/3. When I plug in the -1, B, I get 0. Now C, something interesting happens. H of 2 gets me 2 over 2 minus 2 over 2 over 0. And if you guys remember, we can't divide by 0. So this guy is undefined. All right, let's go to our last page here. Now we're going to look at graphs of functions and finding the values from graphs. So here I have a graph of y equals f of x and y equals g of x. If I want f of 2, this is asking me what is the y value when x is 2. I go to where x is 2, I come up, I go over, my y value here is 3. So I look at g of 0. What is my y value when g is 0? Well, I go g of 0 is here. My y value is -4. I want you guys now to do g of 3 and f of -1. G of 3 was 5 and g of -1 or f of -1 was 0. Now I want to find all the x values for which f of x equals 3. The way I want you to tackle this problem, guys, is I want you to go to where x equals 3, or when y equals 3, because f of x equals 3 means my y value is 3. So here's my y value. Draw a line across. Anywhere your line crosses the function, we have an answer. My answer here is x equals 2. So let's look at it for the g value. When I find all the x values, which g of x is -4, go to -4, draw a line across. Again, I only have 1 on this one, and my answer here is x equals 0. Now let's look at for when x is positive 1. I go to +1. I draw a line across, and this time I actually have 3 solutions. I have -2, 0, and 3. So x equals -2, 0, and 3. It's possible to get multiple answers with these. So now I want you guys to take a look, and I want you all to solve example 6 fully on your own. All right, these were not too bad, but I wanted to point out 2 of these to you. On example C, our graph doesn't fully show h of 10, but we can actually extrapolate and look at the pattern and figure out where it's going. And when you look at that, you can see that you're going towards -13. And then on F, when we look at h of x equals 3, well, when I come up here to 3 and I draw my horizontal line, there is no graph there to connect with that line. So my answer here is no solution because h of x is not defined for x equals 3. All right, guys, thank you very much, and take a look at the practice problems.